We're literally surrounded by iron. It's in the steel that makes up our cities, it's in the cars we drive, it's even in our own blood. But the story of how this absolutely crucial element got here, to Earth, well, it's way more dramatic and mysterious than you might think. So let's get right into it. Yeah, just think about that for a second. The iron in your blood and the steel in a skyscraper, they share the same origin story. That simple little paperclip on your desk, it has a history that stretches back billions of years and thousands of light years across the galaxy. It's pretty wild. So let's trace that incredible journey together. All right, so to really appreciate iron's cosmic story, we've got to start right here at home. Let's first take a look at just how fundamental this element is to, well, everything. I mean, the sheer scale of iron's presence is it's mind-boggling, right? It's in the microscopic hemoglobin carrying oxygen through your blood right now, and it's in the colossal structures that define our entire civilization. But here's the crazy part. Most of Earth's iron isn't even on the surface, not even close. It's deep, deep inside, forming the very core of our planet.
But here's the big twist. None of this iron, not a single atom of it, actually started here on Earth. Nope. To find its birthplace, we have to look up, way up, to the unimaginably hot and violent hearts of massive, long-dead stars.
So the engine that creates all these elements is something called nuclear fusion. You've probably heard of it. It's the same process that powers our own sun. Basically, you get these incredibly high pressures and temperatures inside a star's core, and it forces lighter elements to just smash together and form heavier ones. And when they do that, they release a tremendous amount of energy.
So how does this whole stellar forge actually work? Well, it all starts with the simplest element there is, hydrogen. Gravity pulls these enormous clouds of it together, the pressure builds, and boom! Fusion kicks in, turning hydrogen into helium. As the star gets older and hotter, that helium fuses into carbon, carbon into oxygen, and so on, climbing right up the periodic table. But then, it hits a wall. And that wall is iron. There's a great analogy to help picture the insane conditions inside a star. It's like this. Consider a room full of balloons. If you keep pushing more in, the pressure becomes immense, and they start colliding and exploding. That really gives you a simple but powerful idea of what's happening in there. It's just this chaotic, high-pressure cosmic kitchen where atoms are being slammed together with unbelievable force. And here's the absolute key to the whole thing. Up until iron, every single fusion reaction releases energy, which is what powers the star and keeps it alive. But when you try to fuse iron atoms together, it actually consumes energy. It's a net loss. For the star, making iron is the end of the line. The engine just sputters out, and that leads to a catastrophic, spectacular death. So the star dies in this unbelievably massive explosion we call a supernova. And in that explosion, all the elements it spent its entire life creating, including all that precious iron, get blasted out across the galaxy. This is where the next chapter of our story begins. The journey from Stardust back to a planet. This timeline really puts it all into perspective, doesn't it? We're talking about a journey that took billions and billions of years. An iron atom was forged in a star, then flung into space, and then it spent eons just drifting, until finally it got caught up in the gravitational pull of a new cloud of gas and dust. And that cloud, that was the one that would eventually become our sun, our planet, and, well, us.
So back when the young Earth was just this hot, molten ball, the heavier elements naturally started to sink. And since iron is so dense, the vast majority of it, we're talking something like 85%, plunged right to the center to form the core. This whole process is called planetary differentiation. What that means is that the iron we can actually get to and use on the surface is just a tiny, tiny fraction of what our planet actually holds.
And this core, it isn't just sitting there doing nothing. The churning of the liquid outer core acts like a giant dynamo, generating a powerful magnetic field that wraps all the way around our planet. This field is our shield. It protects us from all kinds of harmful solar radiation and pretty much makes life on Earth possible. So yeah, that ancient stardust isn't just in our blood, it's literally our planetary shield. Okay, so that all seems like a pretty neat and tidy story, right? Stars make iron, supernovas spread it around, planets form from it. Case closed. But a few years ago, scientists discovered a problem, a really, really big one. The logic here is pretty simple. If Earth, the Moon, Mars, and all the meteorites floating around in our solar system formed from the exact same primordial cloud of gas and dust, then their building blocks should be identical, right? The chemical signature of the iron, for example, should be the same everywhere.
But it's not. It's not the same at all. When scientists analyzed rocks from the Moon, from Mars, from all kinds of meteorites, they found the iron was all a perfect match. But the rocks from Earth's crust, they told a totally different story. Our planet has significantly more of the heavier version, or isotope, of iron. Now, an isotope is just a variety of an element with a different number of neutrons. The bottom line is, Earth's iron is uniquely heavy, and it shouldn't be.
And this is the puzzle that has thrown a massive wrench into our whole understanding of how planets form. It's a genuine cosmic mystery. Something happened to Earth, and only to Earth, that fundamentally changed the very nature of its iron. But what?
So of course, scientists got to work trying to solve this thing. For a long time, they had a prevailing theory, but brand new research is challenging everything they thought they knew. So let's take a look at the suspects, shall we?
Okay, so for a long time, the leading idea was that the intense pressure of Earth's core formation somehow squeezed the heavier iron isotopes out into the mantle. Made sense. But recent experiments, and these are incredible, using diamond anvils to simulate those pressures, have basically shown that this just doesn't work. So, that theory's in trouble. And now two new theories are in play. The first one suggests a massive impact, maybe the very same one that created our moon, was so violent it literally vaporized and blew the lighter iron out into space, leaving the heavy stuff behind. The other theory suggests a geological process, much later in Earth's history, churned the mantle in just the right way to bring more heavy iron up to the surface. The jury is still out.
This quote from one of the lead researchers, Nucleosynthesis, really hits home how big a deal this is. He said, "The solution to this mystery must be sought elsewhere. It took a dream team to pull this off." That really highlights the shift, you know? The old theory is out and the search is on. And like he says, figuring this out takes this immense collaborative effort from teams all over the world using incredibly sophisticated techniques to get answers from the tiniest of signals in these rocks.
And really, this isn't just about iron. This is about our planet's entire history. This puzzle tells us that we are still missing a key piece of the story of how Earth became the world we know today. It's a great reminder that science is never settled. It's a process of constant questioning, constant discovery.
And that leaves us with a final, really fascinating thought. Iron is one of the most abundant elements on our planet, and we're only now uncovering its secret history. It just makes you wonder, right? What other elemental stories are locked away in the rocks beneath our feet, just waiting for us to figure out how to read them?